What is the trade-off?
Sorry.
What is the trade-off?
What do you mean by that? What are we losing?
Yeah.
Good point.
You said numerical aperture because you used only half.
Yeah, but we're not, because we're putting two beams down, so we are effectively using all the aperture. So I think the answer, I think time, speed is probably the main thing. But actually we can do this quite quickly. This beat frequency, typically, it can be in the megahertz, so it's not much of a problem from the time point of view either. So I don't think you lose a lot, actually. And this is showing the optical sectioning of this focal modulation microscope, showing how it drops off at 1 over z cubed rather than 1 over z squared. So I think you do seem to do quite well. We haven't seen commercial systems based on this yet, but I know at least one company is working on it. Yeah.
When you say you use 2 half lenses, is that physically 2 different lenses?
No, it's one lens.
Yeah, you just shoot an off-axis on both sides, right?
Yeah, we use one lens and we feed the light into the 2 halves. Yeah. Actually, you know, there are various other geometries you can do, and one of the systems we've also built one where you divide it into 2 annular regions. And you put the 2 frequencies, one down the centre and one outside. So it's got rather different optical properties, but it still has this improved penetration and optical sectioning. Okay, now the next thing I'm going to talk about is source detector arrays. This is I've said a bit about using source detector arrays with the Patran type system. Right, so you can parallelize your microscope and improve the speed. But I've also spoken about, in a confocal, you've got this pinhole. Most of the light you're throwing away because it doesn't go through the pinhole. And actually what we find in practice is that if you're doing fluorescence, you need to open up the pinhole to get enough light, and that basically means you don't get the resolution improvement that you even hope for. So the question now is, can you use that light in some useful way? And it turns out it is. This is a list of various papers that have looked at some of these things over the years, but the one I've highlighted is one that I wrote in a paper in 1988, quite a long time ago. This is a paper I wrote, and it was just before I went to Australia. People often ask why I didn't take this further, and I have to admit I don't really know why. But mainly with moving to Australia and setting up a new lab. But also you have to take into account that 1988 was very early days for confocal. So this was a period when confocal microscope, you know, really took off in the bio area around 1987-88. So the standard confocal was really only taking off then. I'll say a bit about that. It all really dates back to my student Ingemar Kotz, I mentioned several times. I remember he was building a confocal microscope in our lab, and he came to me and said, how do I align it? How do I know when it's aligned? And I guess I hadn't really thought about when is it aligned. Well, the way you normally do it is you maximise the signal. But what he found was a rather interesting thing, was that if he misaligned his pinhole, you know, i.e. it's off axis like in the diagram there, he found that the point spread function gets narrower. Can you believe that? So this was a bit of a surprise to us. So this is the point spread function for a conventional system, this dashed one. The next one is a confocal one that's aligned properly. And then as you misalign it, it gets narrower and narrower. This is what happens. The point spread function gets narrower, but of course the intensity decreases. Here they've all been normalized so that it's unity. It does actually decrease. but there's increased strength of the side lobes. They get stronger and stronger. But also, and probably the most important thing, which we hadn't really fully appreciated the significance of at that time, the effective point spread function shifts sideways, right? So effectively you're illuminating one spot and detecting from another spot. So this is how it works. You illuminate one spot, you detect from another spot, so the overall effect is given by the product of those, which is this curve in between. So really, this offset detector is actually imaging this spot. So what I realised in this 1988 paper was that what you've got to do is to shift that back to there. So this is what we call pixel reassignment. So this is showing again what happens. If we move the pinhole sideways, the point spread function without normalization is given by these dark curves. If you, of course, integrate over all of them, it's the same as if you didn't have a pinhole at all. So that gives this envelope function, which is this blue one, which is exactly the same as a conventional microscope. If we do this reassignment, what we do now is we shift all these curves back to the centre. Right? And then we might think of what happens now if you sum over all of those. So this is what I looked at in the 1988 paper, and I showed that if you do that, this is the OTF for confocal, this is with this reassignment and then integration over the whole array, you see that these high spatial frequencies are actually boosted up. They're stronger than there would be for a confocal. So that was a neat idea, but as I say, I didn't take it any further. So hence this paper was never cited by anybody, I don't think, other than me. And I didn't cite it very much because I was thinking of other things until this paper came along. So this is Jörg Enderlein, and he published this paper in 2010, where he actually did this very same trick. He used an EMCCD, and he processed the signal by doing this pixel reassignment, and he showed how you get this improved resolution, and this was published in Physical Review Letters. So now I went back and started thinking about this again, and so we had a paper. This was after Jörg Enderlein's paper, so 2014. This one, so this one here, what we're showing is what we're investigating is the size of this detector array. It turns out that if you do this reassignment trick with a very large array, you lose the optical sectioning. So you might get better resolution and better signal level, but you lose the sectioning. And you know, sectioning is the main reason you do confocal, so it's not a very good idea. You've got to limit the size of the array. So this picture shows, this one on the left here, shows how various things change as you increase the size of the detector array. Right, so this is 3.8 is 1 area unit, which is what people normally use as the size of a pinhole in a confocal microscope. So what it's showing is how the resolution, which I've labelled half width there, is the blue curve, that gets narrower and narrower as the array gets bigger. You've got to compare that with 1, which is what it will be for a conventional microscope. The detection efficiency, the bigger the array, of course, the more light you pick up. That's the green curve. And the peak of the point spread function is given by the red curve. And this is rather interesting. It increases, of course, as you make the array bigger, but it goes bigger than 1. So this was what we studied in this paper, is how the fact that you can actually get bigger than 1. What you're doing is you're collecting most of the light, And because the resolution is improved, you're squeezing that light, the power, into a smaller spot. So the peak intensity becomes higher than you would get in an ordinary microscope. So if you look at the images you get from this system, the images are amazingly bright. They look very, very bright. Anyway, so you pick some finite, some particular value for the size of the array, typically around 1 area unit, and this will give a point spread function like in this picture here. I've said 3.83 is 1 area unit. 2.75 is what I call the magic number. If you're bigger than 2.75, you start losing optical sectioning. But 1 area unit is still pretty good. Well, this was commercialised by Zeiss. They call it the Airiscan, but it basically works on this principle. So they use an array of 32 elements, and then they use this pixel reassignment type concept in order to merge the signals from all of those detectors. As they're claiming in this paper here, a substantial 4 to 8 times increase in the signal to noise ratio in the final image. So Zeiss are making this. My feeling is that, you know, I published it in 88, so there's no patents or anything on this basic principle. I think that all manufacturers of confocal microscopes will effectively do this in some way or another, because just using a pinhole, you're throwing away most of the light, whereas why not use that light? There are various different ways you can do it though, and so I'm not sure we've even thought of the best way of doing it. But I think all the manufacturers will come out with systems quite soon. Okay, now, so I said that nonlinear imaging, I said that nonlinear effects are often thought of as being where super resolution comes from. These are some examples of this. So incoherent imaging is better than coherent imaging. And it's because of this square law process, the fact you're squaring. The second one, saturable absorber, that was some experiments that my first student, Chowdhury, was doing back. It's in his thesis, we never published it actually. Using nonlinearity has been well known for a long time in things like lithography, optical data storage and so on. The fact that you can exploit nonlinear effects to improve resolution. Multiphoton imaging, if you do SHG or 2-photon fluorescence, you effectively get the resolution of the output light, not the input light. Then there's STED. I'll say a bit more about that in a minute. It's been interesting to follow what people say about STED. There is a view that this is certainly a very non-linear sort of process. Stefan Hell refuses to accept that it's anything to do with non-linearity. I'm not really quite sure why he thinks that he doesn't want it to be thought of as being non-linearity. But anyway, he's always talking about switching or states or various other things, but he's very firm on the view that it's not really non-linearity. And then there's saturation, which has been used in structured illumination. Rainer Heinzmann was the first person to propose that, but I think I'm not sure whether Gustafsson did it first, but certainly gave some very good results. And then finally, these other methods, Palm and Stoll, these are all localization type methods, which again was the subject of the Nobel Prize 3 years ago. So STED, I'm going to go through these very, very briefly. STED, what you do is, I'm sure most of you know about this, you excite the fluorescent dye with a spot of light, and then you use a STED beam, which is basically a donut beam, which depletes the outer parts of that excitation pattern so that it can't fluoresce, and so you only get fluorescence from the central region. So this effective spot is the the region which has not been depleted by the STED beam. So Stefan Hell worked on that for a very long time. Quite interesting that he proposed that first of all in 1994, and they got it to work. I'm not sure exactly the date, but in the late 1990s. So I think probably Stefan Hell deserves the Nobel Prize for perseverance, keeping on trying to do that when everybody was telling it would work. But eventually it did work, and now they get these wonderful results from that. So the best resolution that Stefan Hell has demonstrated, not with biological samples, but looking at defects in diamond, is in the region of a couple of nanometers, using optical light. So it's amazing amount of super resolution. So I don't object to them using super resolution for that method. So nonlinear structured illumination, proposed by Heinzmann 2002, and then Mats Gustafsson published some very nice results on that, and I think I've got a picture of that. Yeah. So this is from Mats Gustafsson's paper 2005. And they're looking here at 50 nanometer fluorescent beads, and here they are using saturated structured illumination. You can see these individual 50 nanometer beads. This is a conventional microscope. This is structured illumination without the saturation. So this is certainly a nonlinear effect. And then localization microscopy. Now, so basically what you do in localization microscopy is if you want to resolve two fluorescent molecules which are quite close together, it's very simple to do that. You make it so that one of them fluoresces at a time. So one fluoresces, and you can localize it to a very, very high precision, and then you make the other one fluoresce, you find where that is, and then you know where both of them are, and you end up with an image which has got a resolution much better than the wavelength of light. That's the principle. It turns out, there were three papers really that demonstrated that approach, all published in 2006 by these three groups. And for some reason, Betzig got the Nobel Prize, and the other two groups didn't. I don't really know about the politics of all this. But actually even more politics is the fact that there's this one above, 2005, which got pretty well to doing the same sort of thing, using quantum dots and the blinking of quantum dots. So they came up with this nice word, pointillism, for this method. So basically the quantum dots are flashing on and off, and then you pick up the you localize one and then another and so on and so on. Okay. Right, so the conclusions of this part: distinguish between true super resolution and others. By true super resolution, I mean you actually increase the spatial frequency cutoff above what you could get with an ordinary lens. Some methods can give an improvement in resolution with an unchanged spatial frequency cutoff, such as pupil filters. Some methods can increase spatial frequency cutoff by a factor of 2, so structured illumination, confocal, source and detector arrays. And some methods can give a further increase in bandwidth, such as so Stefan Hell doesn't like the word nonlinear. He uses the word switching. Switching is to me a very extreme version of nonlinear. Or using evanescent waves is another way. Right, that's lecture 2. Okay, now I'm going to run out of time. I'm now realising, so I think I'm going to jump to lecture 4, which is phase contrast. That probably fits in quite well. Which will mean I'll miss out some things, but you've got the slides. People can look at it if they want. Is that good?
That's
Otherwise,
fine,
I'm going to run out of time.
Yeah, sure.
I think.
I mean, we
could have an extra 15 minutes if you like, but...
well, let me do this first anyway. The third talk was going to be on focusing of light.
More importantly, I think it's important that we have some questions and interaction.
Yeah.
So one of my questions was, you alluded to the Stefan Hell and the resolution in particular, and I think some of the claims that were made about the resolution, maybe Stefan is backing off a little bit on them, especially on the biological side. I think practically getting 10 nanometer or even 30 nanometer resolution in a biological sample when the material that you're going through you don't have very much control over is not very realistic.
Yeah.
Do you have any comments on that? It's different with your nano diamonds. I can accept that you might in extreme cases.
Yeah, there are, I didn't go into the details, but there are restrictions, certainly limitations on these methods. And so things like penetration depth and power levels, and the fact that it might burn up when you're trying to look at it and so on.
Yeah.
So I think that what you say is right, that getting down to 50 nanometers might be a realistic target for some of these methods. I think,
Okay. And would that apply equally to all of them, or
the structured illumination, and I think we're going to find from the pixel reassignment as well, you're going to get down to around the 100 nanometer level with those methods, with some digital processing as well. So without using any nonlinearity type methods, and then maybe an extra factor of 2 improvement by using the nonlinearity type things, either STED or localization.
Right.
This is ballpark.
There's a couple of questions here.
Yeah.
These guys.
You also said about the method to replace the pinhole by a array detector. By a array detector.
Yeah.
I wonder if the full information, also the depth information, should be in the data you collect with the array detector. So even if you use an array detector of infinite size, the information should be there. So
Indeed.
It's
indeed. You're quite right, and so we are working on that. You need to. I think you probably need to do something to make the point spread function asymmetric in depth in order to be able to use that. Because otherwise you don't know whether it came from this way or this way. So you need to introduce some asymmetry. The information is there, as you say. So at the moment, we're in Italy. We're setting up this system where we're using a 25 element avalanche photodiode array, exactly the optimum way to process all the information from those pixels is not clear yet to us. But the Zeiss use a 32 elements photo multiplier array. But you're quite right that there should be some 3D information there that we can use.
Okay, we have another question in the middle here.
Yeah.
You talk about in biological samples, you of course have a limitation on these structures lighting because it will get messed up through the medium. But do you have any experience with adaptive optics, or where you change the phase so that you can kind of compensate for some of this?
Well, I don't have a lot of experience of adaptive optics, but of course plenty of people do. Martin Booth in Oxford, for example, is one example where a lot of work has been done on using adaptive optics for confocal or multiphoton microscopy, and you can certainly got substantial improvements using that. So combining adaptive optics with some of these other methods might. I know that people have used adaptive optics with STED. You can think that you could combine adaptive optics with lots of other things.
Okay.
Any more questions?
Adrian, do you have a question?
Can you comment on STED when you do the photo bleaching? can't you say that in fact the photo bleaching acts on reducing the numerical aperture? So instead we get better resolution, but in fact the numerical aperture, wouldn't that get smaller? Because you photo bleach the exterior of a cylinder.
Yeah, it's not actually photo bleaching. It's stimulating the emission. So yeah, you deplete the carriers.
But can't you mathematically treat that as reduction in DNA?
No, I don't think it's the same. You've got this donut beam.
Yeah.
So the aperture, the Fourier transform of that is still limited by the aperture of the lens that you produce the spot with. Maybe we can. Maybe there's some clever thing we can come up with.
But I think the point there is that the illumination is still diffraction limited.
Yeah.
But the method is of producing an image is somehow gets around that.
Yeah.
It doesn't quite defeat it, but it
you know, so one thing I've often argued with Stefan Hell about is this concept of you know, he always talks about he stresses the fact that STED is a far field technique, and of course it is in the sense that it doesn't use evanescent waves or anything like that. But nevertheless, this STED interaction is occurring in the near field, and it's interesting to note that all these methods that people have come up with for doing super resolution, they're all based on fluorescence, so you know, I mean, I often think, wouldn't it be nice if we could come up with a super resolution method for phase imaging? And after all, phase is a very nonlinear thing, so it sounds as though there ought to be some way of doing it.
So you will ruin there because there's no switch.
No switch, yeah.
So you will ruin
yeah, maybe so.
the debate nonlinear.
Yeah, maybe Stefan Hell's right or wrong. But no, actually there was a Russian, Chichinsky, who was doing some work on super resolution phase imaging some years ago, but it never really quite got it. But, yeah.
Collin, going back to what you said, of course, with the Abbey equation, you are having square root of 1 plus I over IS term, which is what Stefan is really doing, which is very similar to having higher harmonics in SIM to go to nonlinear SIM, which people do accept. It is a kind of non-linear technique.
Yeah, I think he wants to distinguish it from structured illumination. I think it was all part of his campaign to get the Nobel Prize. And,
I think it's different from structured illumination, but not necessarily non-linear sim.
Yeah.
But they call it non-linear sim.
Yeah, yeah. And the other thing is, of course, you find loads of papers seem to confuse non-linear sim with the conventional sim. You know, and so don't always believe what you read in papers, because some people really talk about it.
It's important for people to know about trade-off, because you get further bleaching, so as you localize with a bigger Gaussian beam, you do a stimulated emission in the periphery, you trade off, you get higher photo bleaching rates, which it doesn't matter for nano, the diamond, or some of the more physics applications. And that's a real downside. So there is a trade-off. It's like a triangle of spatial resolution versus time versus photo bleaching to dwell time and fluorophore. That's all got to be taken into account. So it's really the biological question you want to answer, which should dictate the method that you try.
Yeah. Right. Okay.
You better press on.
Yeah, I'll press on, and I'm going to go to phase contrast microscopy. So I've already mentioned this about how if you get a perfect image, you don't see the phase information, right? So how can we do that? We can either introduce a phase, like an aberration, defocus I mentioned before as one example of that, or we can introduce an asymmetry. And I'm going to talk about both those approaches. So there are three main methods of phase contrast. One then is to make the pupil function complex, as I described, and examples of that are Zernicke phase contrast, defocus, and transport of intensity equation methods, and I'll talk about those in a sec, so you know what those mean. Then there's the asymmetry methods, of which Schlieren was the first sort of approach. You know, that's used a lot in aerodynamics and so on, to look at flow of fluids and so on. But it's the basis of a number of other techniques, and in particular I'm going to say something about DIC, differential interference contrast, Namaski, and what I call differential phase contrast, which is another technique based on a similar sort of principle. And then the third class are the interference methods, right? So neither of these first ones are not using a separate reference beam, so they're not interference methods. But there are interference microscopes, holographic microscopes that you can do these sorts of things with an interference beam. I want to distinguish then between really what you might call the coherent methods, which is where you've got a reference beam, and the partially coherent methods where you haven't got a reference beam. And now it turns out then these methods have got some advantage over these ones. You've got an improved image bandwidth. And this comes about just in the same way that the microscope I described in the first lecture. By increasing the size of the condenser lens, we make it less coherent, but we increase the bandwidth of the signal of the system. Secondly, we don't have speckle effects. So with things like the holographic microscope, you see a lot of speckle in their images. And then there's this question though of how you get the information out, quantitative information. It turns out that these partially coherent methods are quite complicated, and as I hinted a bit with some of this stuff before, so it's more difficult to actually get quantitative information from it. So this I showed earlier, the transmission cross coefficient, and the fact that there are these two limiting cases, simplified cases, the case of a weak object and the case of a slowly varying object. Okay, so let's look at some of these systems. One example, one type of microscope I haven't said anything about so far is a dark field microscope, and I'll say a bit about that because as an introduction to Zernica. But what you do in a dark field microscope, you have an annular mask on the input side, and then you have an aperture stop in your objective lens, which basically stops the direct light, and you only let through the scattered light. So in this way you can see very weak structures and so on. And it turns out you can also get the phase information. So what I'm showing here is the top, a weak phase object. We can write in this form, constant background. Let's say we've got a single sine wave on that. The amplitude of the sine wave I've called D, where D is ID, so it's a complex thing, of an imaginary thing, which you'd have for a phase object. And the object spectrum is the Fourier transform of that. So you've got these two delta functions corresponding to the two components of the cosine. And then, because it's dark field, there's no direct light, so this central term disappears, that's equal to 0. And we end up with the final images of this form. And it turns out that this term here is also 0 if you do it by the way I described. This next slide shows this. If you calculate this transmission cross coefficient for a dark field system, you'll see that this quadrant here has got nothing in it. It's 0. And so that means that this term vanishes. We're just left with this, a constant. So you don't see the phase information. You don't see single frequencies in a dark field microscope. What you will see is combinations of different frequencies. So if you've got two frequencies present, then they will interfere with each other, and you will get a signal which comes from this bit of this curve, this surface here. So you will see phase information, but it will be encoded in a rather complicated way. So Zernica phase contrast is like a dark field microscope, except that rather than just get rid of the unscattered light, the direct beam, we change its phase with a phase ring. So we've got an angular mask on the way in, a phase ring on the way out, and the phase ring changes the phase of the direct beam, and then you've got interference between the scattered light with the direct beam. Zernike got the Nobel Prize for inventing this, the reason they use, if you look in your standard book on Fourier optics, they do a sort of Zernike phase contrast, but not using this annular illumination. By using the annular illumination, you effectively improve the spatial frequency bandwidth of the system. And this is the same calculation again for our phase objects. So now we've got this extra term coming in because of this, this is no longer going to disappear. And we get a modulated term on a background. You see that there's a plus or minus here. The plus or minus, you get either positive or negative contrast according to what the phase is that we introduced by the phase ring. Another interesting thing is that there's this C here, a factor C, which if this is less than 1, this is amplified, right? So by making the phase ring absorbing as well as changing the phase, then it actually has the effect of amplifying the phase contrast as well. Well, this is basically how it works. If you've got a bright field microscope, you've got a direct beam, and your phase object is at right angles to that because of this I that appears in that term. And what you actually see is the hypotenuse of that triangle. You only see the length of it, right? So you can see that the difference between the lengths of those two lines is very, very small. So that's why you can't see the phase information. So what you do in Zernike is you use the phase ring to change the relative phase of these two beams so that they're now like this, and now you can see the resultant is much longer than the original, and that's why you can see the phase information. Right, you can calculate these transfer functions for Zernike phase contrast. They look something like this. This is what actually gives you the phase contrast. Two disadvantages. Difficult to get quantitative information from Zernike, and you also get halos around things. If you look at a cell, you see a bright halo around the cell. These sorts of things. These disadvantages, I guess, have to some degree, made it so that people don't use Zernike so much nowadays. Okay, defocus. I've already mentioned about how you can use defocus to look at phase contrast. Effectively, if you think about it, it's very similar to Zernike, really. But instead of Zernike, you just got this step change in phase, whereas in defocus, you've just got a gradual change in phase. Now I'm going to talk about transport of intensity equation. This is quite a popular method at the moment. There's a lot of people researching on this anyway, but there was a commercial system, but as far as I know at the moment there isn't anymore. I guess it was first, the main principle was first proposed by Michael Teague in 1983, and what he showed is that actually if you know the intensity, how the intensity varies in 3D space, you can actually calculate what the phase is, which, they're not independent because they have to satisfy the wave equation as the light propagates. So he came up with this equation, which is actually really only the Icodal equation in a different form. This is his transport of intensity equation. It says that the axial derivative of the intensity is equal to the divergence of I grad phi. This divergence and this grad are transverse ones. That's what the T means there. So what that's saying is if you know what dIdZ is, and you know what I is, you can solve that equation to find what phi is. And then you've got the phase. So that's what he proposed back in 1983. You can expand this divergence of a product, you can expand as the sum of two terms. Very often you can assume that this term is zero, and then it just becomes quite a simple Laplacian of the phase here. So you can solve it by a Poisson solver. Right, this is a nice, beautiful view of the Mediterranean in Italy, near where we live. And the reason I'm showing this is looking at these marks on the reflections on the boat here. So this is a good indication of where the phase of the light, which is changed because of the ripples on the surface of the water, has been transformed into an intensity variation that we see on the side of the boat. So these lines you see that this line here is basically where the surface of the water is like a cylindrical lens, which has got a line focus. And every now and then these join together to make a point focus where that's much more unlikely that that's going to happen, that you get this. So anyway, but this is what we're effectively trying to do, is trying to look at this pattern and from that calculate what the surface of the water is.
Sorry, Colin,
yeah.
But would you get that pattern if you were imaging very fast? Is this because you're integrating over a period of time?
Yeah, okay, so there is a time effect here, yeah, and phase imaging is always like this. If you imagine you've got your biological sample, if it's completely static, then the phase is not going to be changing, and you can measure that phase. If you've got flow and things like that, then the phase might be changing, might it? And then there's time is going to be of the essence, as they say.
Yeah. But could you be imaging too fast? Is the question at the other end?
No, I don't think you can
to be visible
image too fast. No, I think
you still get that image.
Right, okay, so the first image using this method was produced by Norbert Streibel, testicle of rat, 1984. So what he actually shows here is what I call the logarithmic derivative. And so on this previous slide, this is what I call the logarithmic derivative, right? So this is what he measures and displays in that image. He didn't actually solve the equation to find what the phase is. The first paper which actually did calculate what the phase is was this paper by Keith Nugent's group in Melbourne. So this is a cheek cell, and you can see the nucleus of the cheek cell. So they basically solved the equation by actually it turns out you use a Poisson solver twice. Now, of course, the way you do this is you've got to measure the intensity gradient. So you actually have to measure two defocused images, right? So it's a bit similar to the way I described before, which was for a weak object, but this one doesn't rely on it being a weak object. We measure the intensity in two planes and subtract them in order to get the axial longitudinal gradient of the intensity. And actually in practice normally people measure it on three planes because you get a better, more accurate measurement of the phase gradient and a more accurate measurement of the central. You need the I as well as the dIdZ. So they normally do it from three images. Of course, measuring three images takes some time, so we're back on your thing. So if you've got something which is changing, moving, then that's a disadvantage. So there is some advantage in doing it all at once. So that was this paper. So this was with Laura Waller. when I was in Singapore, I was part of the Singapore MIT Alliance, and this guy, George Babastathis, is one of the people from MIT who spends a lot of time in Singapore. He had a student, Laura Waller, who's now at UC Berkeley, and I had a student, Shen Ko. These two girls were good friends, so they used to do a lot of experiments together. And so this was the results of one of their collaborations, where they came up with this idea of using a simple colour camera to get the three images. So basically, you use the three colours to get these two defocused images, and the central one all at one time. So, of course, there's an assumption that the object itself is achromatic here, right? So, but anyway, so you get it single shot, and you can get the phase information. Right, so there was this company, Aisha. Aisha was a company that was founded by Keith Nugent, and they had a commercial system, but as far as I know, they've gone out of business now. But their system, you calculated what phi was, and then you could also simulate the images that you would get by different systems like Zernica phase contrast, DIC, and so on, just by computation. These are some various properties of TIE. It turns out that in particular you can't really get a 3D image, and there have been some papers which have suggested you could, but I've never really seen any convincing results where people have managed to see three-dimensional refractive index variations using this method. And I think that there's good theoretical arguments for why you shouldn't be able to do that. But the important thing is that it doesn't rely on it being a weak object like the defocus method I mentioned earlier. Right, now I'm going to go on to another one, differential phase contrast. I did quite a lot on this when I was back in Oxford. Basically what you do is you've got a scanning microscope, but instead of imaging the light from the sample onto the detector, you place the detector in the backfocal plane of the condenser lens. And what's more, we make this detector structured in some way, so it's got some elements. Here I show what I call a split detector. Very often in practice you use a quadrant in order to do that. But the idea is that this gives this differential phase contrast, because if you've got a phase gradient here, maybe the next one shows this. No, it doesn't. I thought I had one that did. If you've got a phase gradient object, then that's going to shift the beam on the detector, and so if you subtract the signal from the two halves, you get a net signal which is roughly proportional to the phase gradient. So that's why we call it differential phase contrast. So this is an example of a cheek cell taken with that sort of system. So you can see it gives this nice image, a bit like DIC. You've got this bright, it shows phase gradients, right? So bright where the phase is increasing, and dark where the phase is decreasing. And we can also do it in reflection. This is from some sort of integrated circuit, comparing it here with DIC. And it's very sensitive. This is a single monolayer, one of these Langmuir Blodgett films, deposited on a substrate, and we can see this single monolayer quite easily using this method. And now I said that it approximately measures the phase gradient, so what does it really measure? Well, actually what it measures is what I call the phase gradient transfer function. So basically, if you've got a phase gradient, it's going to shift the beam of light sideways, and so you can calculate what the signal ought to be as a function of the phase gradient. And it does this shape that I've drawn here. So this is approximately linear up to some range, and then eventually it starts folding over and eventually cuts off. But it turns out you can actually use other sorts of designs of detector geometry, and in particular we found that using an annular type geometry for the detector was quite good. So these are some results using different geometry. You see that the form of the image is changing. This one you can see with a lot of fine structure. This one you get more of a overall view of the shape of the structure. And you can calculate this phase gradient transfer function for these different systems. So this is, you see various different designs of detector and the response you expect to get from them. So this is a nice one that gives linear response over a very big range here. So that was done in a scanning microscope, and then when I was in Singapore, my student Collin Sheppard, he thought, well, why not do that in an ordinary microscope? Do the same thing by this idea of reciprocity I described earlier. All you need to do is to change the direction of the arrows of the light. So this is now a source of light, not a detector. Right, so of course I've got a plus and minus there, and you immediately think, well, of course you can't have a negative source of light. But of course you can illuminate with the one half, the other half, and then subtract the images, which is equivalent to that. So that's what he worked on. He called it AI-DPC, asymmetric illumination DPC. So you need to take two images for each half of the detector, or if you want to get the phase gradient defy the x and defy the y, you need to take 4 images with the 4 quadrants. So that's the sort of thing he was doing. So this is, you see, these are experimental images, these are the transfer functions, and these are the different, this is just for 2 semicircles, but this is the difference, this is the sum of the two. The sum, of course, is the same as if you had a full circle. Right, now, how can we combine this information? We've got defy the x and defy the y, say, and we want to know what phi is. The problem, if you've got defy the x, you might think, first of all, let's integrate that, and we've got phi. But it doesn't work, because there's a constant of integration. And the constant of integration turns out to be a function of y. Right? You integrate in x, you've got a function of any function, arbitrary function of y. And the same for the other direction. So you've got to come up with some way of combining the defy the x and the defy the y information. And this is the algorithm that we came up with, that we used a lot. So this was developed by our student Matthew Arneson when I was in Sydney, actually we found later that there's something a bit similar in machine vision area, shape from shading, called the Franco-Schalappa algorithm, which is a bit similar to this. And this is an example of applying that. We've got defy the x, defy the y, and we calculate phase from that. This is going back further into the history. Actually, you know, this differential phase contrast was first done in electron microscopes, Deckers and DeLange, so there were also another couple of old things that we found back before our paper was published. DIC, differential interference contrast. So this is quite a widely used commercial system. I might add the DPC is not done commercially by anyone at the moment, as far as I know, but two commercial confocal microscopes have done it in the past. The Biorad and the Olympus both used to do it, but they don't seem to do it anymore. I'm not really quite sure why. Namaski. Namaski, what you do there is you have these Wollaston prisms, and the Wollaston prisms split one beam into two. It's like a birefringent element, so you see these two beams go through the sample, and then they're combined by the second Wollaston prism, and you get interference between those two images. So it's like a sort of shearing interferometer. Now actually there's a bit more to it than that because of polarization. What we do is we have a polarizer which is at 45 degrees. So these two beams are actually polarized at right angles to each other. So they don't interfere with each other when they're in the sample. And this is an important part of how it works. We then have an analyzer at the top which rotates the, you detect the component of the two which is in the 45-degree direction. So that has the effect of combining them and making them interfere. You might wonder what this first prism is for. Why do we need this first prism? Actually, it turns out then that if you didn't have that prism, the system wouldn't behave quite the same, because you've got these 2 points here which would be illuminated from an incoherent source, and so they would be illuminated partially coherently with respect to each other. But with this Wollaston prism here, this light from a single point of the source is split and illuminates the 2 points coherently. So this gives you much stronger fringes of the interference fringes for the Yeah, so
I had a question. You mentioned there that so that they don't interfere in the sample. But if the light is just passing through, that interference is not cached in any way and it has no impact. So are you saying that it's somehow absorbed or interacting with the sample?
No, I wasn't really saying that, but I don't know what would happen if you didn't have the polarized.
If two beams pass by each other, if you had a detector there, yes, you would see the thing, but if they just if there's nothing to detect it, to cache in the interference, then there's it has no impact.
I don't think it would behave the same anyway without the polarizer. Exactly what it would do, I'll have to think more.
Okay.
Yeah. But even the presence of this first prism is it was, of course, in Namaski's original design. He knew that you had to have that prism, but it turned out that other people didn't know that you had to have the prism. And as I was saying earlier, don't believe everything you read in papers. Yeah. Now, what you will need to do is you need to be able to. I say that you've got these two beams that interfere with each other. So you want to be able to basically change the what's called the bias, the phase of the reference beam, so that is done. This is what we call the bias at the top there, and one way of doing it is to just shift the Wollaston prism sideways. Another way of doing it is to use some polarization elements. So different manufacturers do different things on that. The other thing about Namaski is it depends on polarization. So if you've got a birefringent sample, then you can have problems. So for example, a very big example of that is people working on stem cells, because you tend to grow stem cells on plastic, and the plastic is birefringent. Yeah.
And when the light is scattered in the medium, and if you use polarized light due to the scattering, there will be also the phase shift between X and Y component. And thus, how are you able to say for sure it is birefringence of sample because of birefringent, like a phototransparent sample, or because of scattering?
Yeah, I think there's all these problems. I've heard. Yeah. Okay, and you can do it in confocal as well as conventional. Right, so this is an example of changing the bias, so this is where the two beams are interfering in destructive interference, right? So if you've got no phase gradient, sorry, that's the wrong one. The top one is if they're in destructive interference. So if there's no phase gradient, the two beams will completely interfere and result in black. And as the phase changes, you'll move around this bottom of this curve like this. The problem there is that you actually won't know whether you're going this way or this way. So you introduce a bias like this. This is what people used to do. So now you're moving up and down this bit of the curve here as the phase of your object changes. Later on, people realised that actually, if you're recording your image with a detector, then you're much better off to increase the bias until you're at this 45-degree point here, because now you get a bigger contrast, bigger spread here, right? So you get a bigger signal from the phase for a given phase change. So that's what people do nowadays. If you make it right up here, so now the two beams are interfering constructively, then it's much the same as if it's an ordinary bright field microscope. So you don't get very much change in the phase. Yeah, so this is from Collin Sheppard again, and this is pointing out this birefringent thing. So here, this is with a bias of 0, so these regions here, we know they're not a phase structure, they're a birefringent structure. So if you see these regions in this DIC image are actually caused by birefringence, not by phase change. And so this is comparing DIC with DPC. And you see that region doesn't appear in our DPC image because it's not based on polarization. Right, and then we can calculate this transfer function for DIC. And it turns out then that this is the transfer function. The full thing is that top term. And we can calculate both this weak object transfer function, which is this thing here, and the phase gradient slowly varying transfer function that I mentioned is given by this. So this allows us to quantify to some degree what these images mean. So this is looking at the weak object transfer function for DIC. Is this odd part which is going to be imaging the phase information. And this is the phase gradient transfer function. So this shows how the signal you get depends on the phase gradient, right? So you remember for the DPC, we have this anti-symmetric type curve, but this is a very asymmetric curve. It behaves very differently whether the phase gradient is in the positive or the negative direction. So this is altering the effects of the bias, and you can calculate it for confocal and various things. Yeah, now, in order to quantify this, what we found that a good way to do is to do what we call phase stepping DIC. So basically, the image intensity that we measure for a given phase difference between the 2 points, is that equation there. And you look at that equation and you think, that's exactly the same as the normal sort of form of the signal from an interferometer. And one of the big ways that people use to quantify the signal from an interferometer is to do phase stepping. What you do is you measure the signal for a few different values of the phase of the reference beam, and then you solve those simultaneous equations to get the m is the thing we're trying to get out. M of xy is the phase difference, basically. So what we need to do then is to take, say, 3 images with different values of the bias, which I told you how you can change the bias, and then we solve those three simultaneous equations to calculate what the phase gradient is. So this is an example of that. So this is a phase gradient image. And I mentioned before that if you try integrating that, you have a problem because of this constant of integration. This is what you get. Horrible image, lots of streaking, which is caused by the fact you don't know what this constant of integration is. So just like before, we use that same algorithm to calculate what the phase is from d phi dx and d phi dy. So this is an example. So this is from phase stepping DIC. So we take 4 images in this case with different bias settings, and then from that we can calculate what the phase. Actually, the title of that paper is Phase Gradient Reconstructed, but this one has got the phase information integrated out as well. This was a funny thing that we discovered that I was very surprised by, that we discovered by accident. And so Shan, my student, was working on a microscope which had DIC on it. And the one day, she, almost by accident, did TIE, transport of intensity equation, on those Namaski DIC images. And she found it worked still. And we were very surprised, first of all. But basically, this is showing this. So this is 2 different values of bias. And you see that reconstructing the phase from either bias, you get the same answer. Very, very close. So this is really quite interesting. So what this is showing then is you've got these 2 different ways now of calculating the phase. We can either do the 4 different bias settings and do the phase stepping DIC and then calculate the phase from that, or we can use the through focus and use the TIE equation and calculate the phase from that. So these are the 2 results. And you see that they look remarkably similar, so I guess that helps us feel as though this is quite a good measurement of what the phase gradient really is in this case. And this is showing that it works quite well quantitatively, looking at an optical fibre again. Okay, I think maybe I've got to the end of this then. So this is just a summary of these different methods. Zernica phase contrast only really works well for a weak object. It's very difficult to get quantitative information from it. Namaski DIC is good for 3D. I haven't really said about that, and that's still a topic that has not been fully studied, why it gives such good 3D information, but it seems to. We can do phase stepping to get quantitative information, but birefringence can be a problem. DPC turns out to be not so good for 3D as DIC. Defocus should only work for a weak object, but actually we found that it doesn't work too badly even when it shouldn't. I don't really quite know what, it seems quite robust anyway, even if it's not a weak object. And then finally, TIE is not so good again for 3D. So of these methods, really, DIC is probably the best for getting 3D information. I haven't mentioned here in the summary anything about the holographic methods, but of course another way will be to do holographic tomography. It's a good way of getting 3D information too.
Okay, so questions? Anybody? Questions? I have a question. You had the last 2 methods you were comparing there for getting out the phase.
Yeah.
I think there were almost two different algorithms as opposed to.
Oh yeah,
that
that
was
one.
The second last.
This one. This one.
Yes, I was just curious what happens if you subtract these two from each other. Do you just get noise, or is there a real difference?
There is actually a real difference.
Because you've got two independent images.
Yeah. There is. I think you probably. I think we found that the. I can't remember which way round it is now, but I think the phase stepping DIC is slightly better, higher spatial frequency response.
Okay, so you would see the higher spatial frequencies more than that. And when you say higher spatial frequencies, would they be? Would you see sub-resolution information? Like, would you see differences if the structure changed, by 10 nanometers or something? Would you only see a smaller pixel?
That's a good point.
Or would you actually see?
Good point. I mean, there has been this work, of course, where people have used polarization methods to get, sub-resolution type information. Even in Ireland, I remember one of Chris Dainty's guys was doing that, wasn't he? I forgot his name now, but there was a guy in Galway.
Yeah, Chris should have been here, but he got called away at the last minute, so unfortunately.
So there is some indication that you can do some you can get some very sensitive results from using polarization measurements, and. But I think that we don't fully understand what you can do and what the limitations are at the moment.
Okay. While we're on the Irish aspect of this, you mentioned that there's no super resolution method that doesn't use labels, fluorescence. But I know you're going to Limerick on Friday, so you should know that there's an infrared method, and they use the vibration.
Yeah.
So basically, the same idea of switching off the vibration. Using infrared.
Of course I know about that. I mean, I was part of that project.
Right, the European project. Very good. And and of course you know that we also have a method here with Sergey that uses depth information to separate the ones on the surface. So there are ways of doing it that don't require labels, I guess. Any other questions? Here, Adrian?
The split detector. Might not be on this lecture, maybe on the previous one. So when we mentioned the split detector, which is so many people, including your groups, are taking all sorts of rules out of this splitting. I initially thought that you were referring to that split detector which people in Wisconsin are doing, Alfredo Dubra and Joe Carroll, and they enhance the contrast of photoreceptors in adaptive optics of the eye. So they collect the confocal, pure confocal, and with the annular zone, collect the will scatter light, and that is their split detector. So the split detector may mean many things.
Right, okay, okay. So the different terminology. So I don't know about that work, so I ought to look at it. Yeah?
So Colin, at the end, how does Namaski DIC stepping compare with digital holographic microscopy, which seems to be becoming quite popular? Has good resolution, so I mean they
actually
space.
It has very poor resolution unless you do tomography. Because basically, just like in the last lecture I gave, I'll go back to that. Maybe it's worth showing that again. This one. So basically, this one shows 3D transfer functions for different microscopes. So the digital holography is basically a coherent method. So it has a 3D transfer function, a 3D coherent transfer function, which is like this. So firstly, the 3D information it picks up is very, very poor. I once gave an invited talk at a holography conference. It was the opening talk, and the first thing I said was that you know, you have to realise that holography doesn't really give a very good 3D image. And you saw all these guys in the audience, they were all holography people. They all groaned. I've never been invited back to that conference. But anyway, it's true that it doesn't give a good coverage over all the spatial frequencies. It only gives the spatial frequencies that are on the surface of that sphere. And also the size of it. You see that the size of that transfer function is small compared with the size of this, and certainly compared with the size of this or this. Right. So basically, by using some sort of partially coherent system where you've got a condenser lens which has got the same aperture as the objective lens, you immediately double the spatial frequency response of the system. So we often talk about the ABBA limit as being lambda over 2. For holography, it's only lambda. You only get that lambda over 2 if you're doing oblique illumination or fluorescence. Luckily, with confocal fluorescence or structured illumination, you get that factor of 2 twice. So you end up with lambda over 4. And that's why structured illumination can do so well. Yeah. So, but if you do tomography, then it's all different, because now if you do tomography, you start rotating this around, and you can eventually, if you pick up the light that's in the forward direction and the backward direction, you could end up getting the whole of this. In principle, you can do that. But of course, it takes longer to do that. And so one of the big advantages of holographic microscopy, is that it's single shot, so very fast. And they can look at vibrating membranes and vibrating blood cells and so on. Really very impressive pictures. But they are limited in the resolution.
Okay, with that, I think we'll thank Collin and we'll break for. You'll notice that most of the tutors are already here, and they'll be around a lot during the week, and I'm sure they'll be